Okay, so now that we know the different forms of energy and types of energy there are, let's talk about a couple of examples. And we'll start with some conceptual examples to get you a good feeling of what energy is. I think that's a good way to go about it. Before we dive in and look at practical quantitative, we'll look at qualitative examples first and then quantitative ones, all right? So the first one, for example, let's reanalyze our favorite example of a box sliding down a slope. Right, or a person with a skateboard sliding down the slope. All right, so what is the concept over here? Let's not talk about forces. Before we're gonna remember the old way of doing this is which is the object of interest, the slope or the box? The box, right? Even though it's not very exciting, but that's the object of interest. So you identify the object of interest, and then you draw the you draw the free body diagram on it. Basically, you ask what are the forces on it. Now we don't ask what are the forces. We ask what are the energies it has. What are the forms of energy it possesses? Well, we'll release it at rest. All right. So our favorite type is kinetic energy. There is none. Right. And gravitational potential energy is our second favorite one. It's going to be our second favorite one, whether you like it or not. So what is that? That's the energy of height. Does it have any height? Well, yes. So the ground level is where we're going to define as 0. And it has gravitational potential energy. All right, heat energy. Yes, it has some temperature. So potentially yes. Electrical energy. No, I don't think it has any circuits going on inside, nor any batteries. Chemical energy, no, it's not really relevant over here. What else do we have? Light, it's not, well, if it shines, if it's giving out light, if it's a light bulb, it will have light energy. It's going to give out light energy. But no, it's not there. Sound, etc. All of those we're not going to worry about too much. Okay, now that's the initial position. Final position on the bottom, initial somewhere here. Does it have any gravitational potential energy? No. When it's on the floor, let's say this is ground level at the Earth, then there is no more gravitational potential energy. Is there heat energy? Yeah, it has a temperature. Has it heated up? Well, that's a good question. If it does heat up, where does it come from? Probably the friction, right? Yeah, we said we're not going to worry about forces, but even if you don't know about forces, you know about, you know what is friction. And if you rub your hands together, it gets hotter. So it might heat up, okay? So the heat energy might increase a little bit, but let's assume no friction first, right? Our favorite assumption. So just to keep things simple, as you see, physics is very, very simple. Anything complicated, we don't worry about it. That's my favorite way of thinking about it. So let's say it does not heat up. So whatever the temperature is here, it's the same temperature here. So yes, but it's going to be the same. Electrical, you convince yourself. Chemical, no. Light, no. Sound, no. All right. So what does that mean? Well, initially, no kinetic energy, right? And now in the final place, the heat energy is going to be the same, okay? So that doesn't affect things. So the fact that there was gravitational potential energy, where does that go, right? It does nothing else unless it comes down and then it lights up or it suddenly starts barking. Then it has sound, but no, it does not. So it has to go to kinetic energy. And that's why it's faster down here. It starts from rest, and now it's moving at least at some speed, even though if it's not fast, right, some speed. So it has kinetic energy here. In some sense, the gravitational potential energy has went to kinetic energy. So that's a conceptual example. This is how we're going to look at things in the next couple of videos, right? No forces, as you can see, and we'll be able to calculate that. Yeah, the key formulas to remember, I'll write them down a couple of times, right? Kinetic energy is the mass times the speed square. Okay, so whenever you define this is speed square. The gravitational potential energy on Earth is the mass times g times the height of the object. So if it has speed, it has kinetic energy. If it has a height above certain level, it has gravitational potential energy. And spring, the spring, I think I call it elastic potential energy, but or elastic energy, but it conflicts with this, so let me call it spring energy. It's half not half mv squared, half kx squared, and x is delta x squared. Right? This is displacement from equilibrium. Okay, when you define things, this is spring constant, this is mass of the object, this is acceleration due to gravitation, due to gravity, spring constant. Okay, so these are the three formulas, but really the first two is our use. So we'll look at it quantitatively how that works later on, but just sort of the concept first. So example 1a, now how about with friction? Yeah, let's call that 1a and 1b. With friction, well, what would friction do? Well, now let me use red. Can you imagine what happens? Well, yeah, it will heat up more, right? So with friction, so this is the final state with friction. This is without friction. So it might heat up more. Same thing, it has no gravitational energy, no electrical, no chemical. Maybe there is a little bit of, when you go down, maybe there's a little bit of light just over there. So maybe there's just a tiny bit of light energy. Maybe no, but if I'm just saying what's possible if there's lots of friction, maybe it will emit a little bit of light, a little bit of sparks from there. But certainly quite some sound as well, right? All right, now, so what you're going to do is you're going to add up all the initial energy. So you're going to add up everything it initially has, and it should add up to, it might still have some speed as well, so that's still going to be yes. So it should equal to everything like this. So if you care about friction, usually you will not only if you don't care about the friction, only thing that will increase is really the kinetic energy in this example. If you do care about friction, not only will the kinetic energy increase from 0, right? At rest means V equals to 0, speed equals 0, so there's 0 kinetic energy. Not only will kinetic energy increase, but so will the heat energy, so will a little bit of light and quite some sound. Okay, so friction's usually associated with the increase of heat, the increase of light, and the increase of sound. Light, maybe not so much unless you have a lot of friction, but just in general, right? So this is example number 1. Let's talk about qualitative example number 2. How about steam engines? Let's go industrial, right? So what's going on in terms of the energy there? How do steam trains move? First we'll have some fuel, which is maybe coal. All right, so you have you have coal like this, right? And when you burn them, so now when you have coal, you have chemical potential energy. It's stored inside the chemical bonds of things. It has energy stored over there. All right, so now these are going to transform into heat energy. Again, you might ask, how does it do it? Well, no need to worry. This is physics. Engineers will tell you how. But actually, this is so simple. I can tell you how. Just light up the coal. It will turn into heat. Why does it do that? Well, that's more chemistry and more atomic or molecular physics / chemistry going on in there. But let's just look at the macroscopic scale, right? So that's why I say physics is supposed to be a simple subject, and the complexity comes from students trying to ask more deeper questions than you need to ask. It's a good question, and we should answer them, but just let's do one thing at a time. Look at the simplest thing first. So let's zoom out, ignore the microscopic details. So anything microscopic detail, ignore it. We'll just look at the macroscopic details, the macroscopic picture, right? So you start with chemical potential energy stored inside the coal. It turns into heat energy. Now you put a tank of water. So you see any steam engine has to have a whole tank of water. Now the water will increase its heat energy. So this chemical energy becomes an increase in heat energy in the water. The water becomes steam, right? Once it gains heat. And how does that process work again? Don't worry. In fact, we will learn that in 3B of that process. How do you change heat energy into steam? But and if you'll probably learn about that in thermophysics in other classes already, that's good, right? But I'm just curious about what that will do. And that heat energy will turn into kinetic energy. Again, how do you do it? That's an engineering problem, but I'm going to tell you because it's so simple, right? You put a fan. Yeah, it's good enough. Steam will, if you put a shaft, so have the steam go through a shaft, so go through a tube, right? So that's the only way the steam can go. Well, the steam is going to push the fan, which is called a turbine with engineers. So it will start rotating this. Now you can connect this with gears and stuff, mechanical gears and stuff, and to your wheels. So if this turns, the wheel will turn. Right? So that's how you change chemical stored energy, chemical potential energy into heat energy. Steam turns a turbine. This will rotate, right? This will rotate. So now with clever gearing up of this, right? Clever configurations of the gears and all the machinery. Those details is really just really the detailed engineering problem, right? But on a macroscopic scale, you have changed it into kinetic energy. Again, remember, kin kind of means motion in Greek, so it's the energy of motion. Okay. All right, so that's the picture, a qualitative picture of how steam engine works. Now, let's generalize this, let's say, to B, right? So how about power plants? It's exactly the same concept. Now you go one step further. Instead of turning this into an engine that moves across the country, you now do the same. You burn your fuel, right? And it will turn the turbine. Now the turbine is going to store, you change, again, how you do that. That's a complicated issue, but you're going to store it in batteries. This is a very generic form of an icon of battery, and you store it in electrical energy or electrical potential energy. So you store it in electric fields inside this. So the first part is the same. You take fuel, you burn steam, right? You take fuel, or you burn steam, and it stores into electric potential energy, and that can later on be used to do whatever you like. If you want to now take the energy and drive your Tesla, you charge it up, right? Take the electric energy into your car, it's going to take the electrical energy and change that into kinetic energy. So you start from chemical to heat to kinetic into potential. So you have sort of this cycle. Now, is there any energy loss? Is it conserved? At every stage, there is energy loss because the heat is not all going to boil the water. Some of it is going to boil. It's going to heat up the tank as well. So of course, the better isolation, the better, right? But some of it is still going to heat up the tank. Well, if you have a tank engine like that, right? If you have a steam engine, the boiler is going to warm up. Not all the heat is going to warm the water, and you have wasted heat, which is going to evaporate into the air. So you might say, hey, is energy not conserved? Well, depends on your system. If I'm talking about this system, yeah, energy is not conserved. However, this is an open system. So an open system is when energy leaves the system, right? So there's heat going into the atmosphere. Now, if you consider the whole Earth, or even better, the whole universe, nothing's lost. All the energy, if you add up how much energy you actually lose into the air, you add everything up at every stage, that will be conserved. However, if you talk about how much energy went into useful energy, the ultimate useful one, no, it's not necessarily conserved. So it depends whether you're talking about a closed system or an open system. Conservation of energy applies to closed systems. In fact, that's the definition of a closed system. That energy is conserved. If energy is not conserved, you're really talking about an open system. Okay. All right. So that's another example for a machinery one. And I've talked about one already earlier. So just to illustrate, right? So even in our everyday life, biology is really a transformation of energy. So energy can be transformed in one type or another. So let's give another example is if you eat a burger, right? If you eat a burger, technically there's chemical energy inside stored. It's anything that's made of molecules, elements have have chemical energy stored in the bonds, in chemical bonds inside. If you really want to know the details, that's really a chemistry or a molecular physics question. Just is between atoms, you have intermolecular forces bonding. So you have certain bonds bonding the atoms together. There's energy stored there. When you eat into it, it digests it. When you digest, you're basically breaking the bonds. When you break the bonds, suddenly there's no more bonds, right? There was energy holding the atoms together. Now, when you digest it, that's another way of saying, in the physics terms, is breaking the bonds. So where does that energy go? Well, that energy has to go to something. Well, for example, you radiate heat, right? So part of it went to heat. Now you start talking, right? So now you start talking, and part of it goes to sound. You start moving, so part of it goes to kinetic energy. You do a lot of things, right? So if you start moving up a hill, you climb up to the top of a hill. Now you've gained potential energy, but where did that come from? That came from the chemical energy. So that's very important. I've just explained the importance of eating. So you eat, that provides you energy to do the rest of the things. All right. And one more very important example, just to wrap this up as a concept, is you might think, is this list of energy complete? And no, we could discover new energies, new forms of energies. And a very important piece of history is when the law of conservation of energy almost didn't hold. And there was a physicist who decided maybe there's something new going on. First, so imagine I have a heavy atom, and you manage to break it into two smaller pieces, maybe like this, right? So lighter atoms, and you break it into two. Again, how you do that, that's an engineering problem, but let's say you can, all right? So what happens? Initially, this guy is at rest, all right? So let's say somehow it breaks, all right? So we won't worry about how you do that, but let's say it breaks, and then they move at some kinetic energy, right? Kinetic energy 1, kinetic energy 2, right? This guy will move, but at first it's at rest, all right? So what are the total energy? Well, the kinetic energy is 0, so there's no kinetic energy. Let's say they're the same on tabletop, right? They're the same level, so there's no gravitational potential energy if you're both, or even if there is, it's going to match up. So this is not suddenly higher or lower. Heat and etc. You can tabulate everything. There's basically nothing over here, or if there is, it's going to be the same on this side, except for the kinetic energy. So yeah, let's say everything is done at sea level, right? On the ground level. So wait, what's going on? How did you get kinetic energy out of nothing? It seems like it's magic. So what really happened is explained by Einstein, who came up with the formula. He came up with the formula in a completely different way, not this way, but this is one of the most important applications of it, and everyone knows that formula, even if you're not a physicist. It's E = mc squared. Everyone knows how to quote it, but you don't know what it means. But now you know. What it means is he claimed, not from this reason, but this was a verification of this formula in certain sense. He claimed this really from pure theoretical means. He looked at how fast things should move at the speed of light, and he was able to look at this, right? C is the speed of light constant we use of light. It's a very easy number. It's 3 × 10⁸ meters per second in SI units again, right? 3 × 10⁸. It's really 2.998, whatever, 2.99 something. But yeah, it's close enough to a simple number to remember. And that's, so what he discovered is what E is, it's called rest energy, or sometimes called mass energy. He discovered that anything with mass has energy. It does not have to move. It does not have to be at a certain height. It does not have to have a temperature, even if it's at 0 temperature. Sorry, by 0, I mean absolute temperature. Even if you have, like at absolute 0, you have what else? It's not emitting any light, you know, reject everything else. If it has mass, it has energy, okay? So what happened was, when you break a heavy atom into a light atom and you add up the mass, and it does not add up, right? So let's say this is capital M, this is little m1, little m2, all right? So you can calculate what's the mass defect. This is called mass defect. You'll see this again in 3C, again, so we won't do it too probably, but just to illustrate, right? So it's the total initial mass minus the total final mass, right? So initially I have M minus M1 plus M2, right? And you realize there's a number. Okay, now, what's going on here is if you look at the initial energy, you should care, initial and final, you should also care about the rest energy, the energy of something at rest, even though if it's not moving or something, it has energy and it's due to its mass. So the amount of, so what's the change of energy over here? So initially you have E rest, and that's all, right? So E rest initial and E rest final. So here, okay, and plus kinetic energies. Okay. Kinetic energy of one, the first object, and the kinetic energy of the second object, like that. Okay, so I can move this to this side. So this is E rest initial minus E rest final. Okay, is the kinetic energy total, like just the sum of these guys. If each of them is mc squared, so it's the initial energy times c squared minus the final rest energy, which is m1. So yeah, so this is capital M, right? And m1 c squared plus m2 c squared, right? That's the total rest energy in the final state. Total. And I can factor out the c's. So I have m minus m1 plus m2 c squared equals to the kinetic energy. So this is really the mass defect. You see, right? So initial minus final, and this is so delta m c squared, like this. So the total kinetic energy is delta mc squared, is the mass defect times this constant. It will tell you how much kinetic energy you have over here. Now c is a huge number and c squared is an even larger number. So let's say if you add these two mass and this mass, you're just missing a gram. All right. So let's say you're just missing 1 gram of material. So let's say this was 15 kilograms, and this is let's just make it like even easier, right? So let's say this is 15 grams, and this guy is 13 grams, and this guy is 1 gram. Okay, so you add up initially, right? So initially, so what's the delta M? The delta M initially is 15 minus, right, 13 plus 1, right? So you're just missing 1 gram. This time, this is not an SI unit, so I should put it over here. Yeah, also, I just do it in the final because I know these are grams, just for laziness. So how much energy is transformed into kinetic? So you can just estimate that, right? Delta M, right? Let's change that back to SI units. It's 0.001, right? So 10 to the minus 3 kilograms. That's the mass defect over here. And c squared, right? So 3 times 10 to the power of 8 squared, right? That's 3 times 10 to the power of 8 times 3 times 10 to the power of 8. So 10 to the minus 3, just some quick estimates of this, times 9 times 10 to the 16. That's almost 10 times 10 to the 16. So let's just say this is 10 to the 17, okay? And what is it in joules? So 10 to the 17 minus this, right? 10 to the 14 joules. That's 1 and 14 zeros joules, okay? That is huge. So just 1 gram of missing mass, of mass defect, right? It's basically missing mass from 15, right, to 14 total. 1 gram of missing mass. If you are able to change that into kinetic energy, these guys would move apart at huge speed. All right, and this guy is gonna move 10 times faster than this as well because this is basically 10 times more massive than this. But anyway, you have a stream of particles that's moving at 10 to the power of 14 joules of kinetic energy, right? Of total kinetic energy at the end. How can you use that? I have basically just described to you the process of nuclear reaction, right? And how that works. So if you have, so if everything is inside a chamber, so you have things sort of shooting out in all directions with different particles, right? All shooting out in random directions. You create an opening over here. So there's a bunch of particles that will get basically shoot out of this opening. Now with these particles here, you can just make a turbine, which is a wind, like a wind turbine, right? Or basically a fan. And these particles will hit this and turn this very furiously. So in true nuclear reactions, you don't even have a missing of 1 gram. You have missing of 0.000 grams. But just that little bit of mass defect, a little bit of mass difference, multiplied by c squared, gets transformed into huge amount of kinetic energy, which you can then, with clever engineering, connect that to a battery, obviously not with a rope, but connect with gears and stuff, and the clever engineering you'll learn some of it in 3B, how that works, how to change kinetic energy into electrical energy, and you can store a huge amount of electric energy in there. Okay, so we described a lot of concept in basically to give you a good understanding of a good feel of what energy is, and the takeaway is it can be transformed, right? And I'll give you a couple of qualitative ways. However, we are going to focus on just the relationship between kinetic energy and gravitational potential energy. We'll look at some concrete examples from the textbook, and also just to understand how we can redo some of the problems with the energy approach. And you will be the judge to tell me whether this is easier or harder than the force approach.